Hello everyone, and welcome back to this lecture on chapter 2.3. This one's on chemical reactions. The bonding processes that we just went over, those are anabolic chemical reactions. That means that they form larger molecules from smaller molecules or atoms. So if you ever heard of anabolic steroids, you might be able to remember what anabolism means more easily. If you look at somebody that's used anabolic steroids, they're really big, they've got giant muscles because they're building up a lot of muscle tissue. And so anabolism is the same idea. It's the building of larger molecules. The buildup of larger molecules in anabolism requires an input of energy in order for it to succeed. However, metabolism doesn't just work that way, it can proceed in the opposite direction as well. In catabolic chemical reactions, bonds between components of larger molecules are broken down. That releases not only smaller molecules, but it also releases energy. So let's get a little bit more in depth about the role of energy in chemical reactions. Chemical reactions are going to require a sufficient amount of energy to cause the matter that's going through these reactions to collide with enough precision and force that either old chemical bonds can be broken or new ones can be formed. Let's say that you were up on this hill and you're about to push this ball down the hill. Potential energy is the energy of position, or the energy matter possesses because of the positioning or structure of its components. So this ball at the top of the hill that you brought up has a bunch of potential energy because of its position at the top of the hill. When you let the ball go and it begins to roll down the hill, it now releases this energy in the form of kinetic energy. You can see no more potential energy, all kinetic energy. In general, kinetic energy is the form of energy powering any type of matter in motion. And so that's a very simple look at the differences and relatedness of potential and kinetic energy. Now let's look at potential and kinetic energy within the body. In the human body, potential energy is stored in the bonds between atoms and molecules. Chemical energy is the form of potential energy in which the energy is stored in the chemical bonds. When those bonds are formed, chemical energy is invested, and when they break, chemical energy is released. So it's the same idea between this potential and kinetic energy, but sometimes we call it chemical energy when we're talking about body reactions. Notice that chemical energy, like all other energy, is neither created nor destroyed. Rather, it's converted from one form to another. So that's one of the biggest rules in all of life, is that energy can neither be created or destroyed. It's just transferred from one form to another. And so in this slide, I'd just like to introduce sort of the anatomy of a chemical reaction, for lack of a better term. All chemical reactions begin with a reactant, or in this case, reactants, the general term for maybe one or more substances that enter into the reaction. For example, sodium, Na, and Cl chloride were the example of the reactants in the production of table salt. The one or more substances produced by a chemical reaction are called the products. So if you take a look at this graph, this is a graph of a chemical reaction in very basic terms. We can see the reactants and the products, and on the y-axis we can see the amount of energy that is available in each. In this example, we can see what we start with, the reactants, has more energy than what we end up with, the products. So that must mean that some energy has to have been released during this reaction because, like I just said, energy doesn't just disappear. It has to be released or changed into a different form. Chemical reactions that release more energy than they absorb are characterized as exergonic reactions. The catabolism, one example is catabolism of foods that in your breakfast. Some of the chemical energy that's stored in the food is absorbed into molecules that your body then uses for fuel. But some of it's released, and that's released in the form of heat. So your body temperature, you're hot because of this energy that's being released in order to provide the energy that runs your body. And so this is the general form of what an exergonic reaction looks like. Let's just give really general numbers here. Let's say the reactants had 5 joules of energy, okay? And the products end up having let's say this is 10 joules of energy here and 5. Well, if you do products minus reactants, you get a negative number. That means it's an exergonic reaction. All you really have to take away from that is that their start was more energy here on the y-axis. This number is going up and this is going down if you go the other way. So if there's more here than there is here, there was a release of energy and you get exergonic reaction. Okay, in contrast, chemical reactions that absorb more energy than they release are endergonic. We can see that the energy that we have when we start with the reactants is less than what we have at the end with the products. These reactions require energy input, and the resulting molecule stores not only the chemical energy in the original components, but also the energy that fueled the reaction. Because energy is neither created nor destroyed, where does this energy that's needed for this endergonic reactions come from? And what you see is that in many cases, it comes from exergonic reactions. And so what you have is coupled reactions where an endergonic reaction and an exergonic reaction will occur at roughly the same time so that the body can efficiently use the energy that it needs. So you go back, you see an exergonic reaction occur, which releases energy. The body then takes that energy and uses it to build this endergonic reaction. All right, so we've seen, maybe just with our own experience, that reactions can occur really fast. Like you put some baking soda into some water and you can see that reaction occurs really quickly, like fizzes up. Or we could see reactions occur really slowly, like evaporation of water. So what are some things that can alter the rate of reaction? Well, the first is if chemical reactions are to occur quickly, the atoms and their reactants must have easy access to one another. That makes sense. They've got to get close enough to each other to interact. So one way is increasing surface area. Here's an example that you can do at your own house. Pour some water on the table and let it sit there. And you'll note that it'll just kind of sit there for really a while. Now, take your hand, not a washcloth, and sort of spread the water out on the surface of the table as much as you can. And you'll see that it'll pretty much dry much quicker because the surface area has increased and the evaporation can occur quicker. Generally, here's another trend, gases tend to react faster than liquids or solids, and the reason for that is that the molecules are already moving faster in gases than they are in liquids or solids. And the last one is larger particles will react slower than smaller particles, and the reason for that is larger particles just move slower than smaller particles. Okay, so how about this? Have you ever left or forgotten a cup of water on your nightstand for a few days? Well, if you take a look at it, eventually the water will have evaporated on its own. But where might you have seen that sort of reaction occur at a much faster rate? Well, if you add fire to this reaction, let's say you have a pot of water on the stove, you know that that reaction occurs much, much quicker. And the reason for that is because nearly all chemical reactions occur at a faster rate at higher temperatures. If you remember, kinetic energy is the energy of matter in motion. The kinetic energy of subatomic particles increases in response to increases in thermal energy. So the higher the temperature, the faster the particles move, and the more likely they are to come in contact with each other and react. The next one is increasing of concentration and increasing in pressure. So the first one is just increasing in concentration. If you want particles to react with each other, well, putting more of them in the reaction will make this reaction occur quicker. And the other is pressure. So let's just take this example. If you were dancing at a club and maybe there's just a few people, you're pretty unlikely that you're going to step on each other's feet. But as more and more people get up to dance, especially if the music is fast, collisions are likely to occur. It's the same with chemical reactions. The more particles that there are to bump into one another, the more likely this will happen. So that means that chemists can speed up chemical reactions not only by increasing the concentration of particles, just adding more, but also by decreasing the volume of the space, or increasing the pressure in this case. So you can see they have less space to interact when you push down this lever and create a vacuum, which just means less space, increasing pressure. So the concentration, pressure, and temperature, increasing all of those things increases the rate of the reaction. Let's talk about catalysts. So Enzymes are actually protein catalysts, but there's other catalysts that occur. But a catalyst is something that speeds up a reaction without being changed itself. And the most important catalysts in the human body are enzymes. Enzymes speed up reactions by literally grabbing onto molecules and sort of holding them in just the right way so that the reaction can occur. And it's the same idea. These reactions probably would occur, but it would just take really, really long times. And in the human body, they would require temperatures that would be deadly for a human. So in order for our reactions to occur as they need to, enzymes really help that out. And here's just an example. Here's what a normal, this is, by the way, an exergonic reaction. This is a reaction and how much energy you need to input in order for the reaction to occur. Yes, even exergonic reactions require some input of energy in order for you to get over this hump, or what is called activation energy, this energy amount that's required for this reaction to go. But if you put an enzyme in, less activation energy is required, and so you see a lot less energy is needed for this reaction to go to the same product, okay? And so at the end, the enzyme that holds these two pieces of reactants just in the right spot lets go of the product and goes back and can get more reactants, and so this can just continue to keep going. The enzyme is never changed. And so again, enzymes are really important for humans' life and life in general, because without it, the reactions that are required for life to succeed wouldn't happen. And so that's just enzyme activity. And you might see something like this on a quiz or an exam, where it'll show you this exergonic reaction, and it might even just put this graph overlaid on top of this graph and say, what does this smaller line represent? And you'd say, well, that represents the activation energy required with an enzyme. So finally, I'd just like to go over some types of reactions, and this is gone over just a slightly in more detail in the textbook, but I thought I'd still put it in here just to get us started. So the first is a synthesis reaction, and it's pretty simple if you look at it. It's adding A plus B and making AB. Now, I also want to point out that reactions can conceivably go in the other directions, and if this one was to go in the other direction, it would be called a decomposition reaction, where a more complex molecule breaks down to form two or more simpler products. What type of reaction would this be? Exergonic or endergonic? Well, if you remember, breaking bonds releases energy. That would be an exergonic reaction, whereas creating bonds requires an input of energy. That is an endergonic reaction. Then here's a different type of reaction, a little more, I guess, impressive to look at, but really it's actually just a combination of both of those two. And these are called exchange reactions, where really what happens is both a decomposition reaction and a synthesis reaction. If you look, A and B go through a decomposition reaction, and B and C have to go through a synthesis reaction. And theoretically, this can go the other way as well. And so I think that's where I'll leave it for today. Look forward to the rest of Chapter 2 being put up in the next couple of minutes. So see you next time.